Okay, we continue. Our next speaker is Sergey Frolov. We can continue to speak about Josephson junctions. Okay, thank you. Leave the door open. Okay, I observed some attrition in our ranks, our thinning. The toll, the material takes its toll. Okay, so remember me, I'm Sergey, experimentalist from Pittsburgh, and I was talking to you about unconventional Josephson effects. We discussed what makes them special, why are they important. I don't have a good answer to that question because I don't think anything we do is particularly important in the scale of things. But they are interesting because they're deviations from the sinusoidal form of the Josephson effect, discovered by Josephson himself in the 1960s. And they do require, if you just follow my lecture, nothing else about Josephson effect, you think that any junction you make is some kind of a bizarre junction like that, but it does require some effort and thinking of what materials to combine, etc. But there are also instances when, like I already showed you, you think you found something amazing, but there is another explanation, and that explanation is more likely, like this interference effect. This interference effect is interference between several one-dimensional modes in a very narrow junction, a wire, and even one part of the wire could be a quantum point contact, transmitting just a single mode, connecting the two superconductors. But there are other parts in the device where interference between these modes, scattering between modes, takes place, and then you put magnetic flux in, and it's semi-classically as if electron is going around, and it becomes a three-dimensional device. And then supercurrent is suppressed. There could also be nodes and oscillations and wiggles, and those are all mesoscopic interference patterns in a few mode device. And this is done by doing a tight binding model, quant. And I think I largely leave this model in the last lecture. So this is just the first slide. Because I'm going to show you more interference patterns to begin with, and then I want to go towards time-dependent Josephson effect. But there's been a number of papers. This one is 2017. I'll show you a few more where people have observed very clean sets of data, very nice. And remember, blue is zero resistance and yellow is high resistance. So this is a map in magnetic field and gate chemical potential taken at zero source drain bias. So if there's zero resistance and zero bias, that's probably supercurrent. So all this region. And then at a certain field around 1 Tesla, pretty high field, there is this line. Along this line, supercurrent goes to 0 and resistance becomes finite. And then if you keep going in magnetic field, you hit this other region, and then superconductivity reappears. And so that's called reentrance often in the literature, and people give reentrances some significance, like even for pi junction, right? Supercurrent goes to 0 as a function of temperature or field or something, thickness, and then it appears again. And so one is a one phase, like a 0 phase, and the other one is another phase, like a pi phase. Yes?
How certain is this reappearance? Because the blue in the first dome looks much more convincing than the second one. It seems like what is that? Is it conductance maybe?
Yeah, so you say this one is less deep blue.
It's much
light blue.
yes.
This one is deep blue, this one
Yeah.
is light blue. Here it's just like, you know, are you serious? And this
Just some separation, yes.
Yeah, so this is a good question. So when Josephson effect is large, by some measure, like you take critical current multiplied by resistance in the finite voltage state compared to the gap, for large enough signal, you have really truly zero voltage state, and then it switches abruptly into finite voltage state. That's what Josephson junctions tend to do. Now, how it switches, there is some thermal broadening, some kind of you know, stochastic nature to this. It might switch at different points. If you sweep 1,000 times, it will switch always a slightly different point. If you add temperature, it will start switching over broader range. And then if you start shrinking the supercurrent, this switching region on the positive side and on the negative side, they start to merge, and the true zero voltage state disappears. But you can sort of trace this phenomenon to what it was when the effect was large and say, oh, it's just a very tiny signal. It's not really zero voltage, but it's just the same thing. It's still there, right? So this is that's what we're dealing with here, certainly here. At least that's what the authors would want you to do.
So this plot here is basically the resistance, which is maybe some differential conductance at 0 bias, right?
Right, yeah. Yeah, so I'm sorry, I didn't prepare more slides on this paper. I know it very well, but maybe just trust me that, you know, there's superconductivity on either side, and because it closes and reopens, maybe it's a new phase, maybe it's pi junction, maybe it's topological, you know, there's something. So here's another one. This one is mercury telluride. This one is indium antimonide. Again, quantum well, so it's not a wire. It's a whole plane of this semiconductor. And you can see this beautiful data. What do we have here? At different fields. You have these reentrances, and they put pi and 0 here, pi and 0. So on one side it's pi, on the other side it's 0. Here's another one. This is indium arsenide. Again, a big plane of indium arsenide. Again, you can see the pattern. Here they say S-type and P-type. That's for different type of superconductivity. Similar looking data, but here it's not 0 and pi junction. Here it's S-wave, like singlet superconductor, and P-wave, like triplet superconductor. Right? Remember, we talked about triplet, how it would be interesting to see a triplet superconductor. There's some split patterns. And here is a reentrance, right? So this node closes, and this tiny signal, maybe it's not a truly zero voltage state. Here you can see. Or let's look at, maybe here, for instance, right? So you can see this continuation of the same effect, but it's still tiny, and it's not the black color, it's some orange color here. So that's when the switching current is very, very small. And it should be small at very high fields, right? So there's suppression of superconductivity in the superconductors themselves, and then the proximity effect, you derive it from the superconductor, like you have aluminum, and you kill superconductivity in the aluminum, then it is not capable of inducing superconductivity in something else. Okay, so here's another one for those of you working on Van der Waals materials. This is the paper on tri-layer graphene, I think, in a famous journal, my favorite journal. Again, you have the entrance, and in here, look at this. Those were all like 1 Tesla and so on, in semiconductors. This graphene is 8 Tesla. And then this is the reentrance, and this is the reappearance. So, and then they say, this superconductivity here, if you look at the title of this paper, I love it. It says, no singlet superconductivity. So it's like, so superconductivity is carried by 2 electrons, right? Cooper pairs that we we don't go beyond that in this lecture anyways. So 2 electrons, this is quantum mechanics, second semester maybe. 2 electrons, what kind of spin states can we have? We can have singlet, and I don't know, there's also non-singlet, right? There is so many different possibilities. Okay, so anyways, it's a funny paper, yes. But this is not a junction, it's a flake. Right? It's a what graphene people say it's bulk. That's a bulk measure. But you have to keep in mind, their bulk is not so big. The flake is a few microns inside, right? So my PhD thesis junctions were 50 by 50 microns, right? And that was mesoscopic, and this is now bulk. So, there is I think similar phenomena could be taking place. And it's also, graphene is very clean, right? They have Moiré lattices, patterns over microns, beautiful structures encapsulated in pristine dielectric boron nitride. It's very smooth and it's very flat. And so electrons can travel very far without scattering in these materials. Mobilities are very high. Also, it is because it's very flat, if you align the field really well with the flake, then the orbital effect, the depairing effect, should be quenched, right? Because, like I wrote 15 years ago, thickness is 0 in graphene. Well, it's not exactly 0. Maybe it's 1 nanometer, right? And then if you calculate 1 nanometer times a few microns, and how much field it takes to put a flux quantum into this flake, you get 10 Tesla. And so this is where this reentrance is happening, right? So what I'm trying to say is all of these data are potentially explained by the same interference effects, because these 2-dimensional electron gas, 2-dimensional graphene materials are not exactly 2-dimensional. They're slightly distorted. There is bubbles, there is wiggles, and then you put magnetic field through this, there will be interference happening.
Sergey, but you said this graphene is between boron and tritium.
Yes.
So how this ripples be?
It doesn't take much. On the scale of microns, you need to corrugate this sheet by 1 or 2 nanometers, and then you will enclose the flux quantum at 10 Tesla, because they go to enormous fields. So this data is, it takes 8 Tesla to reach this reentrance. And then all of these guys, this is a few hundred millitesla, so this is not so different from the nanowire I showed you. Yeah.
If that's what you're saying, then this effect should be irreproducible across different samples.
Oh yeah, I mean graphene is always like
No, I mean
one sample and then there is an extra paper. I mean, it takes them months to get a stack that is perfectly stacked that they can measure. I mean, for good reasons, they have very few samples.
But then all I'm saying is that this field where the reentrance happens should vary greatly across even the samples.
Yeah, absolutely.
And they do not publish any additional data. Okay, nice physics then.
No, I mean, there are some discoveries in graphene based on one, like for instance, ferromagnetism in twisted graphene is based on one sample. And then actually people try to reproduce and couldn't. So it's an interesting field, yeah. Not unique in this aspect. But I didn't want to talk about this in this course, right? I can give a whole course about this kind of stuff. So yeah, the same with quantum well structure. So imagine your quantum well is perfect, grown in molecular beam epitaxy, layer by layer of atoms without any defects. But even if that's the case, although it's never the case over many microns, because there's dopant sites that can push the 2D a little bit down locally, a little bit up, the wave function will go a little bit like that. Then you put all this stuff on top, contacts, gates, dielectrics, solvents, molecules of water, and and it becomes a little bit wiggly. So take a step back. How many of you have seen this pattern? Just want to know if I go in too much detail. Okay, I'll just go a little quick through this. So this is a Fraunhofer diffraction pattern, which you may have seen in your optics course in your university, and it happens to be what you expect from a large Josephson junction, right? Now, I told you about the nanowire with a few modes. This one has thousands of modes, so it's kind of classical in that sense. Of course, this is a quantum interference effect, but the number of modes is so large that it all averages out. And so if you have a junction, where there's a left side and a right side, we put current this way, and we put magnetic field into the junction, then it encloses flux. As a function of this flux, the critical current of this junction is modulated according to this diffraction pattern. By the way, this is data from the famous thesis of myself, which I've been using for these lectures a lot. And you can see the blue is the data and red is the Fraunhofer pattern. This is an exception to the rule of superimposing theory with experiment, because this is really textbook stuff. And it's just to show you that there are some deviations from this pattern, but it is followed pretty well by real junctions. And so this is the macroscopic interference effect under the field perpendicular, right? And now what all those papers I showed you do is they put the field in the plane. And so in this theory, there is no interference as a function of this field in the plane, because you have to do a flux enclosed by the current loop, and if the field is aligned with current, it cannot affect the supercurrent.
Stupid question. So if I think about this problem classically, I imagine electron starts in some point at electron A, somewhere crosses point to the electron B, and all I'm saying is that depending on how it does so, the actual phase difference that it picks up is going to depend on the cross-section of the total loop, and it can be anything from 0 to the whole surface, so I should see that this pattern is much more smeared, no?
Yeah, so if it's a ballistic junction where electron can really fly in any direction, yeah, then you have to do a calculation like that. This calculation is done in the limit where electrons just sort of go across one-dimensionally, but they can do it at different levels here, so there's a different flux that goes.
Yeah, but still, it doesn't change my argument. I would still say that they can tunnel at any point, and that's why I should see kind of average.
Yeah, so the way this is derived, let me tell you how it's derived, and then let me say that you can calculate these patterns with for different models, right? And then they will deviate from Fraunhofer shape. This is sort of a textbook one. But the way this is calculated is any loop like this dashed line or a smaller one, or if you go around the loop, your phase accumulated around the loop should be 2 pi n, 0 to pi, 4 pi, minus 2 pi, etc. But around any loop. Right? And so if there's flux present, then it kind of modulates the current flowing. So parts of the junction flow current forward, parts of the junction flow current backward to satisfy this requirement. This is a derivation of this formula. Yeah. So, and that's all there is in this problem. Right? So for tunnel junctions, it should really be Fraunhofer. Okay, and then the other one is a two-slit interferometer, essentially. So you have two junctions, one and the other. So you have, imagine you try to pass current this way. Part of the current will go through the left one, part of the current will go through the right one, and you can notice these are classical junctions with sinusoidal current phase relationship, although IC I guess would be negative. Then you write a flux condition around the loop, which has induced flux, which is circulating current here, external flux that we apply, phase difference across one junction, phase difference across the other junction, and this is, again, an integer number of 2 pi due to wave function continuity around the loop. And if you solve this one, you will get a 2-slit interference pattern, like this one. So this is optical analogy. Here is the optical analogy. Squid is analogous to 2-slit experiment. Single junction analogous to Fraunhofer experiment. So you will need this to understand the next few slides. So these are supercurrent interference patterns that they're mathematically analogous to light interference patterns. Are we on board with this? We can survive half an hour with this? Yeah. Okay, so now this is some work from my friends and collaborators at Jülich, Vincent Maurik and Spandan Anupam, his student, where they calculate this effect for non-flat junctions. And it's a very, very simple classical model. It's not a tight binding quantum model like before. This is a very simple model. So what it does is a planar junction, superconductor and a barrier, non-superconducting material. And here now, perhaps to your question a little bit closer, there is width, length, and depth, and there is also direction. So which means current flows along the arrows inside this yellow square. So no current, this example is current flows always in the same direction, and so what you would get if you calculate this would be a Fraunhofer pattern. It's a uniform junction, and you will get at least very close to the Fraunhofer pattern. Okay, so then you see some of the arrows are now looking in different directions, so that's to simulate a corrugated junction. This is a very exaggerated corrugated junction, but I mean, in the model you can make it very, very rough or just a little bit rough. And so you do the same thing, you kind of integrate, you can either integrate current directions or you can integrate flux orientation and say current always flows the same way. That was mathematically equivalent. Okay, so you do some integrals over x and y and flux and this is what you get. So this is a pattern as a function of perpendicular field. So field this way, and it looks Fraunhofer-ish. Not exactly Fraunhofer because there's obviously another envelope here, but a tall central peak and then lots and lots of peaks. And each peak periodicity here is one flux quantum. So you add one flux quantum to the junction, you go through one period. Another flux quantum, another flux quantum, another flux quantum, another flux quantum. And now in parallel field, this is field this way. Yes?
Is it true that the central peak is wider than the other peaks?
Yeah, the central peak is double. Yeah, but that's normal. This is if you look at the actual experimental. So it goes from -1 to 1. Yeah, this is in this function. Yeah. Okay, so you see, this is now parallel field. The periodicity here is much larger. This is about 5, 5, 5. But it's still there, right? I mean,
This one is not up. This one is not up. The right one on the right edge.
Is not what?
Doubled. So the central peak. There
Yeah, it's from -5 to 5, right? And this one is 5. Okay, maybe. I think the devil's in the details. It's not actually 5, it's like 7. And it looks double. Let's do the scientific method. my PhD advisor used to, if you need to tell if the data is completely linear or there is a little curvature, he would print it. I mean, back in the day, and then you would look like this. It works. Okay, so the point is there is nothing in this model except interference, right? And now we already have nodes that go every flux quantum and nodes that go every, let's say, 7th flux quantum, right? And then this is for pretty large disorder. If you reduce disorder, and you can get all kinds of patterns. You can get, this is now parallel field, parallel field, parallel field. Different examples for different disorder realizations. You can have all kinds of reentrances or no reentrances until 20 flux quanta. Some statistics, and here is perpendicular field versus parallel. You can get all kinds of interesting effects, and I can tell you some of these you can find in some of the papers out there in the literature. For instance, Fandan found some. Yeah, I didn't put the references, but I think this is from Charlie Marcus something. So there's an asymmetric pattern, right? So these lobes are larger, these lobes are smaller, and then the paper is called anomalous something, anomalous Markov patterns, right? But here, with interference, you can see one side is brighter than the other. This is again zero field, or this is no, probably plot the amplitude of critical current, right? So this is not that zero bias, just amplitude of critical current. So here is larger, here is smaller. You can have all kinds of interesting patterns. So with disorder, I can explain pretty much everything. By the way, now they're working on explaining my fly junction data and my with the interference effect. So we'll see if they succeed. Okay, that I think more or less it for interference explaining reentrances, etc. Any comments at this point before I move on to the next slide?
I have a question.
Yes.
Coming back to this graphene, the real versus the test. I can understand that this small aggregation will lead to orbital suppression of critical current. But how you can get from this real that I don't understand? This aggregation is necessarily random.
Yeah, so if it's mesoscopic, right? So if it's a really large junction, like we started with metallic junctions, millions of modes, this orbital effect will just lead to depairing, there's just a decay. But if you have a ballistic clean junction, then as the model of Maurik shows, you can have reentrances. You have a kind of a Fraunhofer pattern out of plane and a Fraunhofer pattern in plane. That's one simple way of thinking about it.
You mean that you might have something like just only few channels?
No, only a few of these wiggles. So they don't average out to a decay.
What was the normal conductance?
With
What was the normal conductance?
depends on the experiment, right? Yeah, are we talking graphene or?
Yes, right.
Let's see. Kilo ohms. Pretty high.
10 channels.
That's right.
Yeah, like I said, they say it's bulk, but it's really not necessarily bulk. Okay, and by the way, I should say, this is all just a possibility to explain these metrics, right? It doesn't disprove them. It just says, look, you can get just be careful with reentrances. Okay, so another unusual Josephson effect, higher order Josephson effect. I already mentioned it a couple of times, so kind of shifting gears for a bit. A current phase relation like this. So this one will be the standard Josephson one. And I mean, in Josephson's work, also higher orders are contained in principle, but usually this term here, you can see 4e tunneling. The next one will be 6e tunneling. You expect them to be weaker, a lot weaker than the first term, right? So usually you don't see them, or if you see them, they kind of skew the current phase relation, but they don't dominate. So what we are trying to find is the one where the second order becomes the leading term somehow, or at least comparable to the first order. And there is a way to do this from what I already told you here. For instance, here are calculations by Manuel Jose. For the first order term and the second order term, in those SFS junctions that I studied around this time, 2005, myself. So remember, I showed you that the critical current has these nodes. So there's an overall exponential suppression with thickness of the junction due to scattering on magnetic atoms. And then at the node is where you go from 0 to pi, or to 0 to pi to 0 to pi. And then you can also calculate the second order effect, which is indeed dramatically lower, the blue trace, for instance, here. So this is a log scale, so it's 1 or 2 orders of magnitude lower. So no chance to see it. By the way, it's also oscillating twice as fast because it's sine 2 phi. So you need half the length to get the oscillation going. But for instance, around this point, this one really, this dip is really in principle all the way to 0, to negative infinity orders here. So at this point, in principle, it goes below the blue curve. So when you have a 0 pi transition point, at that point, the higher order terms might come to the front. Right? So you kill the first order term, but the second order term is killed at a different spot. Here. And this was more the first order terms. And so there's been various observations of this effect at the cancellation point. This is an incomplete list, but a fairly trustworthy list, I would say. And so the one way, the sort of the laziest way to look for such effects, different periodicity Josephson effect, is to look at this time-dependent Josephson effect, which was derived by Josephson at the same time as the sinusoidal formula. And so here's the sinusoidal formula. But imagine that the phase difference is now changing as a function of time. So Josephson relation is just stationary, right? Delta phi is a fixed number. But now let's increase it linearly. Turns out that generates a voltage across the junction. That's called Shapiro steps. Yeah, so let me say a few words about Shapiro steps. So this is from Frolov thesis, Shapiro steps. They look like this. Yeah, so the way you do it is you can do the Josephson effect two ways. You can either go in a finite voltage slit and detect radiation coming from the junction, or the more practical one, irradiate it with a frequency, which is called the Josephson frequency. And that tells you the voltage at which these steps will appear. So here I do it by, not by, irradiation is done by AC current. So with no AC on, with AC off, you have this trace, zero voltage state, and then a switch to the finite voltage state. That's just the Josephson effect, how it's supposed to look. And then when you apply larger and larger amplitude AC, you start to develop these little steps, and they are equidistant in voltage. Here we measure nanovolts. And then as you increase the amplitude of the AC, also the amplitudes of the steps increase, and more steps develop. So your switch turns into a staircase. It's a pretty interesting effect. Now, the periodicity, the voltages at which this happens are related to the prefactor here. So if this prefactor is 1, then the voltages are 2E over H. So I just want to say that this is not hard to derive, these Shapiro steps, because this is the entire derivation from Michael Tinkham's book on superconductivity. I don't want to spend time going through it here. Is that okay? But if you need to look it up, it's in Tinkham, literally 1.5 page. This is all just blah, 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 right? So all you need to see is to here. And what happens is that as a function of RF power, the amplitudes of the steps follow Bessel functions. So these are Bessel functions in a purely voltage biased case. Good. So here are some examples of, again, this is from Urbana, this is from my lab in Pittsburgh, different representations of the data. So this is I already showed you. And if I plot the amplitudes of the 0 step, this is 0 step, you can see it goes down with increased amplitude of RF. And then the first step, which will be this one, it goes up. Second one also goes up, and then they start to oscillate, and those are Bessel-like functions. These are also Bessel functions, or Bessel, something like Bessel functions, because you see the 0 step vanishes, then it reappears. The first step is here, and then again here, so you can see that it grows and oscillates and oscillates. Different order Bessel functions. And this is a representation of these data plotting histograms of voltages that correspond to these regions. So this entire black region turns into a line at 0. That's a 0 voltage step. The next line is at 1 in the units of 2E over H. And the next line is at 2, and the next line is at 3, and the next line is at 4, and the next one is at 5.
Wait, sorry, just for a second. Will you please repeat the axis, because I just
sorry. So this is a current bias, this is power, this is power and voltage. So when you plot experimental data, you either have to choose current or voltage on the axis. But to go from one to the other, you have to histogram these points. And they all bunch into these lines. So a way to derive this effect is there is a mechanical analogy. So I gave you an optical analogy between interference of light and interference of supercurrents. And this dynamics follows this mechanical analogy. So you have to assume that the junction has capacitance, and the capacitance is related to charge, and the charge is a derivative of voltage, and voltage is a derivative of phase. So it's phi dot dot. Dissipation is related to voltage, so that's phi dot, and then there's sine phi, and this is the bias. Bias is a tilt of this washboard, and so in this washboard model, the way you get Shapiro steps is you're shaking the washboard, and the ball is the phase. That's a very bizarre analogy. And so the phase has this ball has mass and friction, and so at a certain tilt it starts to roll down the washboard. But if at every time it tries to go you tilt the washboard back because you're rocking it, you kind of stabilize it at a fixed rate. It doesn't accelerate. And that's where the steps come from. Now, this effect is actually useful. I told you none of what we do is useful, but this effect gives us metrological quality measurement of voltage. Used to this day to define what 1 volt is. And the way it's done is time is related to atomic clock, right? So that's to, I don't know how many digits, 13, we can define a second. So which means we can define frequency very precisely. Then we apply frequency to an array of Josephson junctions, and we measure the voltage at the step. And this is so precise to 7 digits or something, related to E, the electron charge, and H bar, the Planck constant. Yeah.
In practice, we just saw that those steps are a bit smeared, so
Yes.
how do they go about
Yeah,
this?
so that's in my lab where we don't care about metrological stuff,
Yeah,
right?
but maybe
So they do a lot better in this. You can buy it and see. These are probably very sharp.
probably my entire savings won't cover this, so probably won't do it.
But yeah, so but the smearing of Shapiro steps will come up today if I get to it. Okay, so now the idea is that these steps give you 2E over H voltages, and then the next term, if that becomes strong, then Shapiro steps will appear at half the frequency, where they're not supposed to be. That's very interesting, right? So you measure the junction, and suddenly you measure something that is charged 4E instead of 2E. And there's papers like this. So for instance here, this group of people from Grenoble in 2004, they went to the 0 pi transition as a function of temperature, like I also had in my work. And right at the 0 pi point, they saw additional Shapiro steps. So this is how it looked. So this is in the units of flux quantum F. This is just 2E over H. These are the primary steps. They're larger, and there is extra little wiggles, and those are the secondary steps. Also, in this junction that gave this result is 17 nanometer thickness. Critical current does not go to 0 at the transition, so this is supposed to be pi 0, and it doesn't go through 0, which means maybe there's a second order effect, and this supercurrent here is actually a sine 2 phi supercurrent, manifesting as these extra little steps. Who is convinced? And extra steps appearing where they're not supposed to be, corresponding to 4E. Supercurrent does not go to 0. Come on, it's convincing. It's in, okay, how about this? It's in physical review letters. The editor said they don't publish wrong papers.
Oh, really?
Okay. So it turns out there is another explanation, which we found, and I'm not saying those Grenoble people suffer from the same explanation, but it's a pretty bizarre thing that basically, well, first of all, we reproduce their results. So here's my Shapiro steps at half the frequency, and here as a function of temperature to 0 pi transition, the 0 step, the 1 step, they all go down, but not to 0, so it doesn't vanish, and the 1/2 only lives in this limited range around the 0 pi transition, where the second order effect would dominate, and then the first order effect becomes so large that it takes over. But what we also noticed, and somebody asked me how smooth and how uniform these junctions are, so there's another answer. What we also noticed is that our Fraunhofer patterns became very bizarre at the 0 pi transition. So here, look at the yellow one. That looks pretty Fraunhoferish. I mean, not exactly, but there is a central peak that is tall and double wide, and then there are smaller and smaller peaks. And then the blue one is actually at the 0 pi transition, and instead of a peak, it shows a dip. And so the idea was that because the junction is not exactly uniform, part of the junction already transitioned into pi state, and part of the junction is still in the 0 state. And so the sign of supercurrent in one part is positive, and in the other negative. And so they canceled. So we swept this flux, and we saw that our junctions have this problem. And this non-uniformity in some effective parameters is very tiny. 10.4 nanometers versus 11 nanometers, 6 angstroms in effective thickness of the junction. Almost nothing, 6 angstroms. If I build a 6 angstrom step ladder, it will take a long distance to gain any altitude. Okay. Okay, so how is it related? So this is an explanation also for 0 and pi, homage to this famous experiment from unconventional superconductivity where they made these corner junctions, and the wave function of superconductor was complicated, this D wave shape. And so when you tunnel here, you get a plus sign, and when you tunnel here, you get a minus sign, you get this cancellation as well in that experiment. And the optical analogy to this is that you cover one of the slits with a pi shifting plate, the optical analogy, or you cover half of your single slit with a pi shifter. And so light that goes here doesn't have a pi shift, light that goes here does, and at the center you get destructive interference rather than constructive interference. That's a 0 pi junction. And this is a 0 pi squid. So in a 0 pi squid, this interference pattern shifts maximum at 0 to minimum at 0. Okay, skip this. Right, so what is the alternative explanation here? Well, when you do have 0 and pi regions, imagine drawing a loop around here. If you draw a loop around here, you pick up 0 here, you pick up pi here. It means you may have to circulate some current to satisfy the 2 pi periodicity of the wave function here locally. And this vortex will be a half vortex. So it will have phi naught over 2 in it. And then another boundary will have another one of these vortices. And so there will be these vortices living there in the junction at each 0 pi boundary inside the junction. And then we found a paper from 1987-88 where they put a vortex, a half vortex, in a squid, in a loop. These folks at IBM, Van Neste and collaborators, and what they saw was half integer Shapiro steps due to a half vortex moving inside the squid under the RF irradiation. Huh? Yeah, so you see here the unusual steps. This is actually simulation. This is the experiment. There are some very high frequency steps that are not supposed to be there.
So this is alternative explanation.
Yes.
How to distinguish between them?
Why you have to do the Fraunhofer pattern and see if there is a minimum at 0 or not. So Herman Sergey told me that his were Fraunhofer, but there was no data in that paper. I think I looked at his thesis and he has some. So it could be just the two possibilities for the same looking data. But you have to do the Fraunhofer patterns at the 0 pi transition. Right? If you are 30 millikelvin off, it will look Fraunhofer again, or 100 millikelvin. Okay, so what happens is, remember I told you this washboard potential, and you rock it, and you hop from one minimum to the other at fixed intervals of time, and that's what gives you Shapiro steps. So that's what happens in a kind of a squid, in a junction, without any flux applied. You just hop from one minimum to another, and that gives you integer Shapiro steps. And then if you put half a flux quantum, and you calculate the potential, there are these half minima that appear, and you hop twice as frequently. And that's what gives you half integer steps. Okay. So we'll skip this stuff. And just to drive the point home, there are more explanations for half integer steps, more than just sine 2 phi and half a flux quantum. Because, for instance, here's a paper from 1998, Conrad Leonard and his advisor, Alan. And this is a niobium indium arsenide niobium junction where they see half integer Shapiro steps, and they are attributed to some non-equilibrium quasi-particle dynamics. And I'm not going to tell you what it is, partially because I don't remember or never understood it exactly. But just to tell you that here's another explanation for half integer Shapiro steps. So half integer Shapiro steps seem to be a really bad smoking gun evidence of anything. Even though they look so appealing, right? It's something so unusual that appears very rarely under very specific situations, but more than one situation. And so, having found this problem, this is from, I already mentioned this document to you, my thesis. This is a kind of a concluding chapter. No evidence for the second order Josephson component because the signatures, the Shapiro steps attributed to inhomogeneity in the junction, essentially. Again, you also see the theme, right? Disorder, interference, and homogeneity mimics a lot of the effects, a lot of these interesting effects. Tony Leggett was in my thesis committee, and when he read this, he said, why is he graduating? He's not done. He's not found the sine to phi effect, right? But I of course, in your PhD thesis, you point the direction. So I said, sine to phi should exist near the first node of the ICD dependence. And that's because we mostly studied very thick junctions where second order effect is even more suppressed. And only towards the end of my thesis, they found these first node junctions. So I graduated in 2005. And in 2006, they found the sine to phi effect in these junctions. Now, a published paper only in 2018 because everybody was very busy. But the data is from 2006. So basically, I was looking for sine to phi here. And then the non-uniform junctions were here, but they were non-uniform, so I couldn't see the effect. Then they made them a little more uniform. They added a layer of copper in the junctions in Chernogolovka. And they became more uniform. And then we repeated the current phase relation measurement. Now, this is not Shapiro steps. This is really put a junction in a squid, put flux, and you see that it's doubly modulated. And then at the 0 pi transition, really the current phase relation doubles its frequency. So this will be the real sine to phi effect. And that's because here the thickness is shorter and the second order effect is less suppressed. So if you make a uniform junction here, you can see it. But maybe this is some artifact again, right? But by now you shouldn't believe anything I show you. So we confirmed this effect 4 different ways, right? And this is probably the most exhaustive study I've done in my life. I mean, I was already gone, actually, but they did it. And then I helped them write the paper. So in addition to the current phase relation, look at these patterns. So this one looks Fraunhofer, right? And then as you move closer to the zero pi transition, it develops a second modulation here as well. Right? So it's like having a sine phi Fraunhofer and a squeezed one at sine 2 phi. And then superimposing the two of them, you have extra shoulders, extra bumps. Here are some simulations. So the purely sine 2 phi Fraunhofer will have this modulation at half a flux quantum. And then also critical current did not go to 0. And also we had half integer Shapiro steps. But like I said, those two signatures by themselves are not unique. But with these patterns and the current phase relation, so this is I think we can put a check mark on the sine 2 phi dominated Josephson junction at the zero pi transition, right? From 4 different measurements. And in Pittsburgh, we also found a very strong sine 2 phi more recently. Paper is on archive. These junctions are indium arsenide 2-deg. So a plane of indium arsenide with aluminum on top. Actually, junction is templated by the nanowire. We place the nanowire on top, and then we put aluminum down. We call it smash junction because the wires are kind of smashed into the. It's a pretty clean device, and what is interesting, it has a very large second order effect. So you see the second modulation and these kind of oblong side peaks as well. Would be a signature of sine phi plus sine 2 phi, current phase relation. So one is modulated by 1 flux quantum and one is half a flux quantum. So this is a model where we put this kind of current phase relationship and do the interference pattern calculation. So you can see how it goes. And these curves are the ratio of IC2 divided by IC1. So there is no IC2, it's a Fraunhofer pattern. And if there is a lot of IC2, it looks like this. Now, what is weird about this experiment? One thing, maybe it's not I shouldn't tease you with this because I didn't introduce it enough, but this is measured without any magnetic materials or without applied magnetic field. So we are not near any zero pi transition. We are near zero field. This is a very small flux, it's a millitesla. So this is strange to have such a large apparent second order Josephson effect in a pretty standard junction without any special regime. Nothing should be suppressing the first order, or nothing should be enhancing the second order. Now, it is a clean junction, it's a ballistic junction, so electrons travel without scattering. In such junctions, we expect higher orders, but we expect first order, second order, third order, etc. And here it looks like the second order is really anomalously large, and the third order is nowhere to be seen. So I don't know the answer to this question, but I'm just saying it's odd. So maybe there is another explanation that I'm not thinking about, except I thought about a couple. For instance, let's think about the non-uniformity again, and those interference patterns created by non-uniformity. In some of our junctions, we noticed after fabrication there was this dark strip. So here is the junction. This is all etched away. This is the junction. This is the bottom superconductor, top superconductor, and this is the nanowire that defines the junction. And about a third, maybe a little less, of the junction there is this darker strip. from some fabrication that we did. And so the hypothesis is, what if inside the strip supercurrent is higher and outside the strip supercurrent is lower? Kind of like diffraction grating. Right? And remember what happens in diffraction grating. If there are 5 periods of grating, there'll be one big peak, then 4 little peaks, then another big peak, and then 4 little peaks. So if you want one big peak, one small peak, one big peak, one small peak, you need something like this. So this is what this model gives. So this ratio JC2 to JC1 is now JC2 here and JC1 here. And it gives very similar patterns. Again, disorder effect, interference effect of disorder. So of course in our, so we realized this before writing the paper, so in addition to this pattern we also did the current phase relation and the Shapiro steps and all these things. So this does seem to be a very large sin to phi, unexplained. But I'm just saying here is another way to get this pattern. And here is leaping for a bit into the topological junctions, which I still hope to talk about today. So here I want to make a point about the x-axis here, right? So you see the pattern and you say, well, this must be 1 flux quantum, this must be 2, this must be 3. I don't know what it is. I'm just sweeping some current in a magnet. I can turn it into millitesla. That's pretty okay, unless my magnet is nonlinear. But let's trust the millitesla. But it's very difficult to say where this point is. That's because the geometry of the junction does not always correspond to the area of the junction. For instance, in a very clean junction, electrons can travel underneath the superconductor, and so the area can be larger. There's also London penetration depth effect, so usually the area is not very well known, and we actually get the area from this period. So usually it's okay, because the pattern is so clear, like even this one. And then I say, well, okay, so this is my main period, and this will be half a period. Can you guys follow that? Would you allow me to make this leap? Right? I don't know this axis, but I want to write flux, like here on top. I want to write 0, 1, 2, 3. I just go, well, here will be 1, here will be 2. Why? Because where the nodes are. I mean, this is not the best example because it's a complicated pattern, but if we go back to the famous work of me, it's pretty clear Frolov pattern.
In this case, yes.
Yeah, I don't even know what my field was here anymore because I completely removed it from the graph.
No, here I don't object. It makes sense, but on that plot, kind of.
Right. Yeah. So exactly. The point is that, I mean, when it's a more complicated pattern, you need some kind of physics assumption to make this statement, and so there's a number of papers. For instance, this pretty early paper, very nice, from Goldhaber-Gordon group at Stanford, where they made a topological insulator Josephson junction. And in topological insulators, what we can have is, in Josephson junctions, what can we have? Majoranas. Right. So they thought maybe we have Majoranas, right? And why did they think that? Because their pattern was kind of interesting. It had a shallow node and then a deep node, and then kind of 2 periodicities in the pattern. this is one of the first TI Josephson junctions. It's a pretty important paper, but they basically argued that, look, for Majorana, it's not sine 2 phi plus sine phi. It's sine phi plus sine phi over 2. Because Majorana is a 4 pi Josephson junction, so it's sine phi over 2. It's in the other direction. But what I'm trying to say is, if you don't know this axis, how many flux quanta per millitesla, then how can you tell sine 2 phi sine phi from sine phi over 2? You actually cannot tell. Yeah.
Well, there's a slight difference between those two cases because here in the first case we expect sine phi to be the dominant harmonic, and in the second case we expect sine phi over 2 to be the subdominant one, no? Like qualitatively, phenomenologically.
Yeah, I see what you're saying, but I think from our modeling, look, so depending on the ratio, you can get.
Yeah, I mean,
right?
right now I'm just saying that if I accept that it's either sine 2 phi because of, I don't know, 0 pi junction or Majoranas, there's a qualitative difference, I would say.
Yeah, oh, I agree with that, but it could also be just in homogeneity.
Certainly.
And then it can have any shape.
Of course.
So the third option is probably
And then
very powerful.
Don't they specify the actual size of the device to just have an idea whether it's?
Yeah. So the size, look, here's width 1.5 microns, right? But what I'm saying is the geometric size can be a factor of a few off from the interference size.
Like really a factor of 2 you can have?
Yeah. So in a thin film, penetration depth could be a micron.
Okay.
For instance.
Fine.
So,
Okay.
Okay, so maybe skip this. Just to say that we did the current phase relation in these junctions, and we did all the 4 measurements here, Shapiro steps. Here's the 3 halves, 5 halves, 7 halves, Shapiro steps, and so that's by my criteria that you do 4 measurements and they all tell you it's sine to phi. This has to be sine to phi. But why is it so large? I don't understand. Maybe one of you can explain it. Okay, so the last topic of my 3 lectures is, we already started entering it. It's the Majorana-Josephson effect. This Josephson effect is probably the most bizarre. And let me just say it up front that I don't think has been observed in any measurement. So just, remove that. Ambiguity. Maybe you're tired of my mind games by now. But the basic idea is like this. Remember, 4 pi already appears in the simple calculation of Andreev bound states that connect the 2 superconductors. And remember, there's already a branch that is kind of a positive and a negative branch, and both are 4 pi. And so if you were living on one of the branches and you were not allowed to leave it, you would have 4 pi Josephson junctions always. So this is sort of the origin of it. Now, the idea is that Majoranas prevent you from leaving this branch. What we need to have is, this is just illustration purposes, device from my lab with a nanowire, 1 superconductor and another, and imagine Majoranas on each end of each superconductor. So there's 1, 2, 3, 4 of them. And I'm not going to derive it here, but you just have to believe me that whenever the phase difference between the 2 superconductors is not pi, then the 2 Majoranas here, their wave functions are overlapping and they're hybridized, and they are not Majoranas, they are split. They're the two energies split. They are just Andreev bound states inside these junctions, and they carry normal Josephson current, like we talked about for 4 hours by now, with me, you and I talked about 4 hours. But there is one special point. When the phase difference is exactly pi, then the two Majoranas become decoupled by topology. The matrix element becomes 0, especially if the other two are far enough away. They actually, Professor Nazarov calculated the 4 Majorana system, one of the first, and showed that if the 2 Majoranas on the ends are close, then this is not even correct. But if they are far enough away, it decouples, and then you're kind of bound to this branch, either the black branch or the green branch, and that depends on the parity, how many electrons you have in this junction, an even number or an odd number. Yes?
So you say you're bound to a single branch when phi equals pi. Now I look at the plot and phi changes from minus 2 pi to 2 pi on this branch.
So you bound either to this branch, so you just go like this,
Yeah.
or the green one.
Okay. And which phi equals to pi?
Oh,
It's a different phi.
yeah.
Different.
It's the axes are drawn incorrectly. I'm sorry. This is the pi point, where they are degenerate. Yeah. Thank you for noticing it. Yeah. I had this slide for a while. Never noticed. Yes. I'm sorry. This is the pi point. This will be well, 3 pi point, pi, and this one will be the other one. The minus pi. Yeah, that's a little confusing, right? I apologize for that. At this point, you cannot cross branches. Okay, so then, so why not make a squid and just see the 4 pi squid oscillation, right? That's because you can fall down from a branch. You're gonna start going, so you go, say you go on the green one. You go down, you're in the lowest energy state. Here you cross, you didn't cross to the black one. You keep going, but then up, fall down, and so it resets, and it becomes 2 pi. You fall down pretty close to this point. So any slow measurement, like I change the flux and then I measure current, change flux, measure current, will not reveal the 4 pi periodicity. And so what do we need to do is a fast measurement. And a fast measurement is Shapiro steps. Again, right? So Shapiro steps. Okay. Yeah, so indeed, there's theory papers, there's experimental papers that say, oh, we have some evidence of the 4 pi effect in Shapiro measurements. Now, remember, the 2 pi, the sine 2 phi effect resulted in extra steps appearing. The phi over 2 effect results in steps disappearing. Right, so instead of this conventional Josephson junction, steps every 1, 2, 3, 4, 5. This is a RSJ simulation done by my student, Sanchayeta Moody. Now in the unconventional junction, if this is the current phase relation, it's only the even steps and no odd steps. No step at 1, no step at 3, no step at 5, etc. So you need to find missing, you need to observe the disappearance of steps.
Do they disappear completely or they're just...
Well, the more disappearer they are, the Majoranier the data.
So this is simulation, this is not...
This is a simulation, yeah. And you see how sharp they are. Yeah. This is like 0 temperature, everything simulation. This is another simulation just to show you the more our work is like last year. Just actually, I think she did it during COVID. Wow, time flies. She couldn't go to the lab, so she did this. This is from 2012. Basically the same thing, right? This is a standard regime. And this is, maybe this is a little mixture, a bit of conventional, a bit of unconventional. This is more unconventional, and you can see there are 2, 4, etc. steps. This is from Fernando Dominguez and his collaborators. Yeah, it's a simple model. Just put Majorana and do Shapiro steps. Okay, and of course there's experiment, also 2012, and here it's a pretty complicated sample. It's not one nanowire, it's kind of they etched a whole array of them, put some superconductor. There were some interesting things about that sample. For instance, the resistance to the gate was 900 ohms, if that tells you something. They apply magnetic field. You remember, from Majorana you need field. You need to break the spin symmetry. So they go to higher and higher field, and look here, the first step anyways, just the one step, seems to be completely gone. Here it is at 0 field, the first step. Here it is at 1 Tesla, at 2 Tesla. The other steps are still there, so pretty good superconductivity survives to high field. But the first step is gone. Anyways, in one bias direction, in the other bias direction, maybe not completely gone, but here more gone.
Also, the third step is still present.
Yeah, the first step is still present. Of course, there was a theory to explain how, I think by Manuel Jose, the guy we already highlighted here, that if the rate at which Majoranas jump down, and there's also Landau-Zener tunneling to some other states, if those rates balance out just the right way, the first step will be gone, but the second one and all the higher ones will be there again. Okay, so needless to say, what often happens is people look for something bizarre predicted by theory, like, oh, the step should disappear, and they find it. But if they looked for it before the theory told them to look for it, they would also find it. And so sometimes the order is just reversed. So for instance, here's from Javad Shabani, also has missing or suppressed first step. For instance, here, well, it's not completely gone, but it's kind of over this range of powers anyways, it's gone. You can see the trace is here it's still there. And then orange and green, it's not there. It could be many different things, but it could not be Majorana because they did not apply magnetic field. Right? Here's another one from Benjamin Sesepe, who will be one of your lecturers as well next week or so. This is not even a Majorana junction. Like Shabani's one was the semiconductors and spin-orbit interaction and all those ingredients. This one is just a piece of metal, and what they show here is many steps disappear, one step disappears here. The first step should be here. So this region here is the second step, for example. Or this is actually maybe even more steps. This should be the first, second, third, fourth, 5 step disappear. And what is this? This is a heating effect. You kind of apply a ref, and then you switch the bias, and it switches all the way to the 5th step. It locks onto the 5th step, not on the 1st, not on the 2nd, not on the 3rd. So there's this other way to get fractional steps. In any case, to make the first step disappear, but then the stakes go higher. So this is a paper again from mercury telluride. We already talked about mercury telluride. here. So this is from Lawrence Molenkamp, and Dirk Lapwijk was visiting there. He's a big expert on superconductivity, and Seigo Tarucha from Japan is also involved in some of this work. And so here what they say is, look, not just the first step disappears in this experiment, but also first and third and the fifth and maybe even others. And what is plotted here, you can see this is not a current voltage characteristic where we can see the steps. These are those histograms, right? So they took the voltages from their data and they binned them into these bins, and they plot how often you see data inside this bin. So when you have a fixed voltage step, you expect a lot of points in the bin. And when you have in between the steps, you have kind of a gradual background. So these ones look pretty sharp peaks. These ones look also reasonably sharp, but look at this pretty low frequency. If I convert this frequency into energy, this is like a microvolt or so, and in temperature, this is like 10 millikelvin. So this is a very small energy scale. I'm driving with this very small frequency, and I have my Shapiro steps that are not steps really, but they're kind of just wiggles like this. They're kind of wiggling slowly. And so you see that instead of these sharp bins, you have these gradual smooth bins. And that's because the steps are not vertical and horizontal, but they are just kind of bumps. So you have a straight line, and on top of it you have bumps. And a histogram is a wonderful way of visualizing that, but you have to know where this is coming from. And so, yeah, looks like some of the bumps are not there. Some bumps are higher and some bumps are lower. So, in my group, we reproduce this. So here's, for example, the histogram we have. So bright is a lot of data points, and blue is less data points. And so this will be a Shapiro step. These very sharp lines are Shapiro steps. And now here what we have is the first one is missing, the third one is missing, the fifth one is missing. This is supposed to be fractional Josephson effect. Every other step is missing, except here it is also done at zero magnetic field, where we don't have Majoranas, and we don't have reason to expect the fractional effect here. Also, if we tweak around the gate and the flux, we can make other steps disappear. For instance, the first and the second and the fourth seem to be gone here. And another setting, we have the half integer steps pop up again. So we were looking for some steps missing. Here we got extra steps. And this is all one device, the same device, right? Just looking around and changing frequency and changing things like that. So I think the explanation here is that you see here is 7 gigahertz, large energy scale, sharp lines, clear steps. If you look at those current voltage characteristics, really steps, you can resolve them. Here, low frequency, very blurred data, and then something else is happening in the device. So if I remove the steps, the curve is not exactly smooth. It already has some bumps from some mesoscopic physics, some bound states, some disorder, some resonances, right? Again, the same theme. Some mesoscopics comes in. And if those extra bumps line up with Shapiro bumps, they can kind of cancel each other. So one wants to bump down and the other one wants to bump up, and the result looks smooth, and ooh, the step is gone. 5 minutes. Yeah, so we did a model for this effect, which is very a simple model. It derives from the same RSJ model where, remember I told you junction analogy to a mechanical system with capacitance and resistance, and a bias is the tilted washboard potential, except we allow the resistance to be dependent on bias. So I told you there are bumps. So something like this. For instance, if a resistance is a differential resistance now, and it changes with the bias. So this would be maybe some kind of Andreev reflection or bound state at that bias. And then I apply Shapiro step, RF frequency, and at the position of this bump, the step is reduced. Now if I add to this some smoothing, due to temperature or other effects, the step may be completely gone. So this bump made the step go away. And of course you can make the whole, it holds over the range of powers, and you can make the odd staircase go away by making a bunch of bumps, or the even staircase go away. And this is what I'm talking about when I say the data is pretty gradual. So this is what these steps really look like in experiment. They are not really a staircase, right? They're just a bunch of bumps. And when you just plot the histograms, they look very clear and convincing. But when you look at this, you get different ideas. So important to show your data, show a lot of data, but also in the right presentation. Yeah.
When you are saying that resistance depends on bias, it's current bias?
Current voltage, I mean, it's simpler in the model to implement current bias, but we adjusted it to fixed voltage.
It's a non-linear.
Non-linear.
It's not Ohm's law.
Non-linear, yeah, exactly. Not an Ohm's law.
Can you just test it experimentally?
Yeah. So if you read our experimental paper, we found all kinds of. Yeah, I can show you actually. There is one. Yeah. So look, this is you already recognize Fraunhofer-ish pattern. So the blue region is supercurrent, so 0 voltage state, and the stuff above it is finite voltage state, so not supercurrent. But look, there are all kinds of things there. It's not smooth.
No, I mean in the normal state, there is no superconductivity. Do you still have
Well,
this
this is-
resistance?
Oh yes, of course. This becomes some kind of quantum dots and things, but it's a suppressed superconductivity completely, right? Like apply a large field or something.
Or temperature?
Yeah, but they don't look so sharp and they're not at such low voltage. So I think these are related to superconductivity, but they are not, well, they're like, for instance, multiple Andreev reflections would show up there in this regime.
But for superconducting system, for Josephson, you do have this super non-linear.
Yeah. But it's also non-monotonic, right? It's not just like switch and then go, but there's some other stuff.
But inside the model, you put a parameter that shoots.
Yeah, this is a very simple model. Yeah, here is just a parameterized like that. Yeah, and it's arbitrary in the model. This is a very simple model. Okay, so that's all I got. Let me just go back all the way to the first slide of this course. So my entire life is flashing in front of my eyes, literally. Yeah, so we talked about unconventional Josephson effects. And let's just remind ourselves what they were, at least according to me, the ones I'm interested in, my entire scientific career, essentially. Pi junction, where it's a sine function that is flipped. Phi junction, actually also due to Professor Nazarov and his postdoc Tamahiro Yokoyama. A current federation that's shifted left and right, and also up and down. Different IC plus and IC minus. Topological junction, which is a 4-pi junction, right? Wider one. And higher harmonic dominated junction, right? Easy to get a ballistic junction that has higher harmonics, but they don't dominate. This one dominating, and by the way, I didn't have time to talk about it, but if it is due to ballistic, the sine of sine to phi is opposite to the sine of phi. So one of our papers measures the sign, and the sign is negative for the amplitude of the two phi terms. And so now let's think about what of this. So when I started my PhD, none of this was established. I think pi junction was just established, or indirectly, not with a phase shift of pi. So in the meantime, pi junction has been established. I believe phi junction has been established. Higher harmonics were found, and this is the only one that we are pretty far, I think, from demonstrating, at least 2024, that's my assessment. But overall, if you zoom out, and if you're not just in the Majorana tunnel, we're doing pretty good. Just 20 years, and look at all the discoveries that we made. So with that, I'm gonna finish, and thanks so much for sticking around and for listening.
Questions? Well, then that's it for today, I suppose. Sorry.
May I ask a provocative question?
Sure.
Mostly you just stated that the experimental methods in use, which all has been invented like in 60s, 70s of 20th century, are not quite adequate for this stuff. Why? I understand that people who approach 60, who are 70, 60 years old use these methods. Why didn't you switch?
You mean to like RF microwaves?
Yeah, you could, for instance, measure inductance with geometry. Is simple, not sufficiently simple RF.
Yeah, we are doing that as well.
Okay.
That's the short answer. The longer answer is, I think those are also not artifact free. Once you get to them, you will find some alternative.
They are known artifacts. Okay.
Yeah. So yeah, I think I like the simplest to implement experiments, because if we're already confused with those, like we're just transferring the problem to a more complex domain.
Okay, if that's it, let's thank the speaker again.
А на завтра объявлено?